Hello everyone, welcome back. In this video, we'll be taking a look at functional limits. Now that we're done with limits of sequences, we're going to look at limits of functions. So when we're looking at functional limits, there are various cases to consider. The first and probably the most important one of them all is finite case. So if you have ever seen a definition of a limit before, it would have probably been this one, this pretty famous one. So let's see what it basically means. It says that for all epsilon greater than 0, so this looks so familiar as the one for the sequences, but instead of there exists an n, over here there exists a delta greater than 0. So remember that n is a large value, but delta, n is large, but delta is small. It's a small value. So there exists a delta greater than 0 such that 0 greater than the modulus of x minus a less than delta. So here a is the, let me write it, I forgot to write this. Here is what a is. A is as x approaches a. So there are a few technicalities here. First, x can never be equal to a. That's why we have 0 right here. We have 0 because x can never be equal to a. X can never be equal to a in this definition, and that's how, because that's how mathematicians decided it should be. And a has to be in the domain of f of x, of this function right here. So those are the two technicalities we have. So let's go back to the definition. So we have, for all epsilon greater than 0, there exists a delta greater than 0 such that x minus a is less than delta, then f of x minus L is less than epsilon. So let's take a look at this graphically. So remember that when we're drawing, when we're looking at things graphically for sequences, we used to draw the number line like the axis like this way, because the definition of a sequence was it had the domain of the natural number, so we could never go back. But for functions, we can draw it this way. So I want you guys to note that it's a subtle change. So if you have this random function right here, and we have this as our L, and therefore we'll have this as our A, and therefore since fx minus L less than epsilon can be written as f of x being less than L plus epsilon and L minus epsilon, and remember this is our f of x, this line here, we can have L plus epsilon and L minus epsilon, and x minus a, modulus of x minus a less than delta can be written as x being less than a plus delta and a minus delta. This, let me use another color there, this a minus delta and a a plus delta. So these should be evenly spaced out. Okay, let me just do that again, make it less confusing. These should be evenly spaced out. A plus delta. This is a. Right. So this is for, so basically this is the definition if you look at it graphically. As as um, as epsilon becomes smaller and smaller, our delta needs to become even smaller and smaller. So remember, from for sequences, as epsilon became smaller, n needed to become larger for the sequences to go into the tube. But right here, as epsilon gets smaller, delta should even become smaller. For example, consider this graph where we have a L here and a here, and we have a large epsilon. of a quite large epsilon 1 and epsilon 1, L plus and L minus. Therefore, we could do away with a large delta, a plus delta 1, a minus delta 1. But as our epsilon becomes smaller, as it becomes smaller, for example, epsilon 2, L plus epsilon 2, and L minus epsilon 2, our delta also needs to become smaller, because remember that whenever epsilon becomes smaller, whenever epsilon becomes smaller to this, that was, sorry for that, whenever epsilon becomes smaller to this, our delta should be such that we should cover this part of the graph. We should always cover this part of the graph that the epsilon is enclosing. So let me just highlight it. We should cover this part of the graph, and to cover this, and therefore our larger delta will not work, because it's now covering this part of the graph that it shouldn't be covered. It's covering this part of the graph it shouldn't be covered. So our delta needs to become smaller. We can find a delta 2 here and a delta 2 here. As our epsilon becomes smaller, our delta needs to be smaller. But note that once we have this delta 2 right here, any smaller delta will also work, because it's always covering this part of the graph, although it's excluding uh, parts of the graphs that need not be excluded. But any smaller delta will also work, because it's always covering the part of the graph on the x-axis that's being covered on the y-axis. But a larger delta will not work, because it's covering part of the graph on the x-axis that is not covered on the y-axis. So I hope you guys understand the definition. Let's go ahead and take a look at the finite infinite cases. So the finite case was the most important one. So these are also like quite important, but they're not as important as the previous one. So we'll take a look at examples of all of these cases in the next video. So it says that limit of f of x as x approaches a finite number a is then it's plus infinity. So remember, whenever it approaches infinity, we use epsilon whenever it approaches a finite number L, but we use m when it approaches infinity. So for all m greater than 0, and note that we use delta when x approaches a finite number, but we will use n in the later sections when x approaches an infinite number. For example, when x approaches infinity, then we won't use delta anymore, because delta and epsilon means small, and m and n means large. So for all, this definition says that for all m greater than 0, there exists a delta greater than 0, such that x minus a less than delta, then f of x is greater than m. So graphically this sort of looks like this. So if we have this graph 1 over x as x, and we take this as 2, let's take this as 2, or let's just consider 0. So as x approaches 0, the finite number 0, as x approaches 0, f of x tends to infinity. So for all m greater than 0, for any m we find, for any m we put, as x approaches this 0, f of x will always be, this is f of x, remember, f of x will always be greater than m. And the case for negative infinity is quite similar. It's the exact same definition. It's just that we have a change right here, where f of x is less than m. So if you consider, for example, this example where 1 over x, remember the graph of 1 over x is sort of goes like this. So as x approaches 0, it goes off towards negative infinity. For whatever m we put, we get that there is a f of x, there is a part of the graph f of x which is always less than m. So that's the finite infinite case. As x approaches finite number, f of x heads off to infinity. So let's look at the infinite finite case. So as x approaches an infinite number, then f of x approaches a finite number. So since we're dealing with a finite number over here at the limit, we'll come back to epsilon. But since we're dealing with an infinite number as here as x approaches infinity, we'll replace delta with n. So so remember when we had a finite case, we had epsilon here and delta here, but when we had a finite infinite case, we had a m here and a delta here. Now we have an infinite finite case, so we have a since it's the end product here is finite, we'll start with epsilon, which is small, and then since x approaches delta, we'll use n. So it says that for all epsilon greater than 0, there exists one single n such that for all x greater than n, f of x minus l is less than epsilon. And the case for negative infinity is exactly the same, except that over here we have for all x less than n. So let's take a look at the infinite finite case before we end the video. So the infinite finite case, it says that the limit of f of x as x approaches plus infinity or negative infinity, and so in the infinite case we have four sub cases, let's call that sub cases, where x approaches infinity and x approaches negative infinity, and f of x approaches plus infinity, negative infinity, plus infinity, negative infinity. Sorry about that. Right, so let's see what this definition means. So limit of f of x as x approaches infinity, it approaches when first we'll look at the case when it approaches plus infinity, then we'll look at negative infinity. So when it approaches positive infinity, for that means we go back to m. Since this is both infinite case, we'll only use m and n, because m and n are large and epsilon and delta are small. That's how I want you guys to remember it. So for all m greater than 0, there exists a n such that for all x greater than n, f of x is greater than m. So let's take a look at this graphically. For example, consider the graph x square. Simple graph, right? F of x equals to x square. So for all x, and let's say we put this as m, so there exists some n for all m greater than 0. There exists some n such as this right here, such that for all x, remember this is the x-axis, so for all x, x, for example, this x equals to 10, x equals 15. So for all x greater than n, for all x values greater than n, f of x, the graph f of x here, we'll find the graph f of x being greater than m. And now if we find even a larger m, we'll find even a larger n such that for all x greater than n, f of x is greater than m. And when x approaches negative infinity, as x approaches negative infinity, consider the graph f of x equals to negative x square. Even in this case, we have a m right here and a n right here, such that for all x greater than n, we'll find an f of x right here, f of x that is less than m. Remember, we're going to negative infinity, so we'll find an f of x right here which is less than this m right here. And if we go and find a even smaller m, we'll need a larger n, but we'll always find a larger n such that for all x greater than n, f of x is less than m. And the case for as x approaches negative infinity is quite similar. So let's just look at one example to make it clear. So we look at the same one, f of x equals to x squared, but now x approaches negative infinity, so x goes this direction. So in the previous case, we were looking at the positive direction as x approaches infinity. So in the next case, in the case we're looking at now, we look at x approaches negative infinity, so in the opposite direction. So for any m we put, for any m we find, we'll find a n such that for all x, remember now it's less than n. For example, n is -2, we'll find an x, for example, -3. So -3 is less than -2. We'll find an x less than n such that f of x, f of x right here is f of x right here is greater than m. You can see that f of x is at a higher position than m, so we can find one f of x greater than m. So that's what basically the definitions for the functional limits. So hope you guys have enjoyed this video. See you next time.